I want to give us this third installment of our consideration of bases for vector spaces. And I just want to, very briefly recap the fundamental ideas. So basis just means that we've got a linearly independent set of vectors that spans the entire space. And what this means, right, the immediate consequence of this is that every single vector u in the space can be expressed uniquely, or decomposed, expressed, expanded. These are all sort of interchangeable words for what the basis allows you to do. But the important thing is that it can be done uniquely. Has an expansion in terms of the basis vectors v1 through vn. And the uniqueness part here refers to these coefficients, right, the c1 through cn's. And, this is really just saying how much of u points in the direction of v1, so to speak. When it's just a regular old basis where all you have is linear independence, a formula for the CIs, well, you don't really have a great one. Basically, you have to do a lot of algebra, solving linear systems of equations to figure out formulas for the C's. So this isn't, it's not great. It's not a very efficient way to do things. So then the question becomes, how do we make this more efficient? And one way that we can make this more efficient is what we did last time. We can look at orthogonal bases. Right, and the idea here is that you're not only a basis, but it's a basis plus pairwise orthogonality. Right, in other words, Vi is orthogonal to Vj whenever I is not equal to j. Alright, so now you've got them pointing in all sorts of different directions, and they're all orthogonal. So once you have this, well, then we get something really quite impressive. Then U has a very specific decomposition in terms of these basis vectors, and this is what we saw in the last video. These coefficients can be very explicitly calculated. Right, so your C1 is U1 dotted with V1 over V1 dot V1. And this is going to be true for all of these coefficients on all of these basis vectors. Oops. It should be a dot Vn in the direction of Vn. Alright, and what we saw last time is that this is really a sum of projections. Alright, so this is really quite nice, and what I want to do now is to try and make this a little bit better. All right, remember the only thing I said that you could take umbrage with here is the fact that we have to divide by v1 dotted with v1 or v2 dotted with v2 and so on. And v1 dot v1 is really the same as magnitude v1 squared. So I left off the last video asking what value of the magnitude of v1 would make this a really convenient calculation. And hopefully you arrived at the fact that if the magnitude of v1 is 1, well, then this is a very nice calculation. All right, so if the magnitude of v1 is 1, well, then the projection onto v1 of u is u dot v1 over v1 dot v1. But remember, this denominator is just the magnitude of v1 squared. So if the magnitude of v1 is 1, then there really is no denominator there. It's just 1. And so what you get is the following remarkable formula, that the projection onto v1, its coefficient, right, the size of it, is just found by taking the standard dot product. So there is a name for these bases that have orthogonality plus the magnitude of every one of the basis vectors is 1. So this is a special kind of basis, and this is referred to as an orthonormal. Oops. Orthonormal basis. All right, so this is a collection v1 through vn. We say it's an orthonormal basis, which I usually abbreviate to ON. It's an orthonormal basis if, first of all, it has to be a basis, meaning it spans the entire space and it's linearly independent. And further, they are pairwise orthogonal. Whenever I is not equal to j, you get that they're orthogonal. And right, this is the brand new extra condition. The magnitude of vi is equal to 1 for all I. Alright, so if you have an orthonormal basis, this means that they're all pairwise orthogonal. So they all point in as different can be directions relative to one another. And they are all unit length. They're all length 1. And, you know, this observation that we had up here about orthogonal bases, and the theorem that we had in the last video about orthogonal bases, can be souped up to a theorem about orthonormal bases. Right, so if v1 through vn is orthonormal, meaning an orthonormal basis, so let me be more specific, is an orthonormal basis, then any vector u in the space, right, whatever vector space you happen to be talking about, can be expressed as, well, u is now equal to u dotted with v1 in the direction of v1 plus all the way through u dotted with vn in the direction of vn. And now we're saying exactly the same thing here. I don't want to make you think that something has fundamentally changed here. We are still saying that this is a sum of projections. The only thing that's changed is that in requiring that they have unit length, these projection formulas have a nicer formula. That's all we're really saying, right? The denominator is now 1 in all of these projection formulas, which makes them look like these really simple dot products. Okay, so this is really the big thing that I wanted you to see about why orthogonal and orthonormal bases are very nice. If you want to know the coefficients of some vector in how it's expanded with respect to an orthonormal basis, all you have to do is take dot products. And so this is very, very nice. Let's see an example of how this could be used. Here we have a problem where we want to figure out the coordinates of a vector 1, 1 with respect to this basis 3, 2, negative 2, 3. So the first thing I want to do is, let's just go ahead and check if these vectors are orthogonal. 3, 2, dotted with negative 2, 3. And, of course, this gives negative 6 plus 6, which is 0. So they are indeed orthogonal. However, all right, let's check the magnitude of one of them. This is going to be the square root of 9 plus 4, which is root 13. Definitely not a unit vector. All right, so this is an orthogonal basis. Right, this is orthogonal, but not orthonormal. That's not the end of the world. Right, so what this means is that if we want to figure out these coordinates, right, we want to figure out the coordinates of 1, 1, in terms of 3, 2, and negative 2, 3, well, if we were doing this, directly, maybe, so let's just look at what it would look like if we tried this directly, right, just naively diving in and seeing what would happen. Well, then we would have 3c1 minus 2c2 should be equal to 1. And we would have 2c1 plus 3c2 should be equal to 1. And so, you just solve this thing however the heck you want to. And you do a lot of work, and you come out with whatever the answer is, just using algebra. That's annoying. All right, that's a polite word for what that is. Let's say it's annoying. So now let's use our theorem. Right, so use our theorem about orthogonal bases. And our theorem says that u here is going to be this vector 1, 1. U is equal to u dotted with v1 over v1 dot v1 in the direction of v1 plus u dotted with v2 over v2 dot v2 in the direction of v2. All right, so we're being asked for specifically the coordinates. Right, find the coordinates of this thing. And so our answer is going to be these. Right, those are our coordinates. So let's go ahead and calculate these one by one. So u dot v1 over v1 dot v1. We know what u and v are. All right, so this is 1, 1 dot 3, 2, I think was v1. Yeah, 3, 2. Over 3, 2 dot 3, 2. And so this is going to be 3 plus 2. Upstairs is 5. Downstairs is 13. All right, so the first coordinate is 5/13. And now the second coordinate is, let me draw a line to demark that. This is going to be u, which is 1, 1, dot negative 2, 3, over negative 2, 3, dot negative 2, 3. And so this is going to be negative 2 plus 3 is 1 over 13. And there you have it. These are our coordinates. So what this tells us is that 1, 1 is equal to 5/13 in the direction of 3, 2 plus 1/13 in the direction of negative 2, 3. Okay, so there you have it. Very, very fast way of doing this calculation. Now, when you're only in 2 dimensions, this might not seem like it's the fastest thing in the world. However, once you even move to 3 or 4 dimensions, calculating dot products is so much faster than trying to solve, 3 by 3, 4 by 4 systems of equations, which can really be quite tedious. All right, so this is very, very quick. It's a very efficient way of calculating these things. And the last thing I want to say about this example is that we didn't have an orthonormal basis. Right? Remember, we had magnitude square root 13. So we don't have an orthonormal basis, but we can change that. So we can change our basis to an orthonormal basis. The hard part is orthogonality. Once you have orthogonality, it's really easy to make an orthonormal basis from that. We're just going to replace 3, 2 by 3, 2 that's been unitized. So 3, 2 over square root of 13. In other words, 3 over root 13 and 2 over root 13. And do the same thing with negative 2, 3. All right? And then you will have an orthonormal basis, which is really quite nice. Okay? So the hard part is orthogonality. Once you have an orthogonal basis, it's really easy to generate an orthonormal basis from it. All right, so given an orthogonal basis, V1 through Vn, we can form an orthonormal basis. Say U1 through Un, just by setting Ui equal to Vi over its own magnitude. All right, so just unitize all of those vectors, and that will do it for you. All right. So again, orthogonality is the hard part. Orthonormalness, right? Generating an orthonormal basis from an orthogonal basis is really quite straightforward, really quite easy. All right, so the next thing I want to talk about is the first, sort of exotic example of a vector space. We've really only looked at, R2, R3, standard sort of spaces that you can just sort of, visualize. What I want to do now is consider the first sort of more complicated vector space. This is denoted by P2 of 0, 1, the interval from 0 to 1, that is. And this is the space of all polynomials of degree 2 or less. And you want the variable x to be between 0 and 1. This is an example of what's known as a function space, because everything that lives inside of it are functions. Alright, so this thing is a vector space. If you remember back to linear algebra, the idea of a vector is just anything with a direction and a magnitude, right? So that notion is a little bit weird for a function. So you want to be a little bit more abstract when you talk about vectors. And when I say a vector in this case, I really just mean that it's an object that can be rescaled. So you can multiply it by a scalar, and that operation makes sense. and you can add it to another thing and have the addition make sense. Alright, so I'll show you some examples of what I mean by that. First, some examples of vectors that are in here. I could take p of x to just be equal to x. Right, this is an example of a polynomial of degree 2 or less. This has degree 1. Right? The degree of this polynomial is 1. And so it is in P2. I could have another polynomial called Q, and this might be, 1 minus x squared or something. Right? This is degree 2. And so this thing does live in P2. I could have r of x just be, I don't know, a constant. Let's say it's just equal to the number 4. Right? This is degree 0. All right. So all three of these things do live inside of P2. And notice that if I were to multiply any of them by a constant, right, so let's say I look at, I'm sorry, not r. If I look at, I don't know, 6 times p of x, well, then I get 6x. And this is still a polynomial of degree 1. So this is back in P2. And if I take, p of x plus 3q of x, right, so I'm looking at a linear combination of two of them. Well, this is just going to be x plus 3 times 1 minus x squared. And so this is 3 plus x minus 3x squared. And this, again, is a polynomial of degree 2 or less. And so this is back in P2. Right, and so one other thing we would need to check from this is that the 0 polynomial, which I'll call z of x, which is just everywhere equal to 0. I'm not sure if I've used this notation in class before. If I have, it was from a very long time ago. This triple equal sign means is equal to for all x. Alright, so this is what this triple equal sign means is that you are stating that z of x is the polynomial that is equal to 0 everywhere. Alright, so this polynomial is also in P2. Again, it's a polynomial of order 0, of degree 0. So it is degree 2 or less. And it is in P2. And so these three properties together, the fact that you can rescale anything, which is right here, and the fact that you can take any linear combinations of two things that are in there, and the fact that 0 is in there, loosely speaking, these three things together tell you that P2 is a vector space. Right, it is a little bit more complicated than that, but this is generally the idea. It's a vector space. Alright, in other words, that means that we can refer to the things inside of P2, namely all of these quadratic or linear or constant polynomials, as vectors, which I did right there. Alright? So, the idea that I wanted to introduce here is the idea that P2 is a vector space, and we've just been talking a lot about bases, so let's ask a simple question. What is a basis for P2? All right, can we come up with a basis for P2? In other words, can we find a collection of polynomials degree 2 or less for which everything in P2, so every polynomial in P2 is a linear combination, linear combo of these other polynomials that we found. Right? In other words, this is just what it means for something to be a basis, right? So the idea here is, the first thing that I want to mention here is that you have a sort of standard form for what something in P2 has to look like. Right? Saying that it's a polynomial of degree 2 or less means that it absolutely has to look a certain way. Right? So P2 of 0, 1, this is a characterization of P2. Right? Its definition is just that it's all polynomials degree 2 or less. However, we know exactly what polynomials have to look like. All right, so this is going to be the set of all things that look like ax squared plus bx plus c. And here, the only restriction is that x has to be between 0 and 1, which is told to us by this, it's the fact that it's a P2 of 0, 1. You could have other domains there, right? You could have other intervals. I just happen to pick 0, 1 because of what we're going to talk about next. However, this idea is still sound, right? What it's saying is that all these polynomials of degree 2 or less, they all have to look like this, right? They have to be quadratics, and possibly A, B, or C could be 0, right? Any combination of them could be zeros, and this will give you the fact that you have linear functions in there and constant functions in there. Okay? So, right, what is the idea here for this basis? Well, let me get rid of the fact that this is a characterization. By characterization, I just mean another way of viewing it. Right, everything in here has to look a certain way. That's what that means. So, here is my idea for a basis. In viewing the polynomials of degree 2 or less in this sort of standard way, what we're really saying is that we have this thing written as a linear combination already. All right, so the coefficients in this linear combination are the coefficients a, b, and c. And the functions that are in the linear combination are x squared, which is a polynomial of degree 2 or less, x, which is a polynomial of degree 2 or less, and sort of hidden here is the constant polynomial 1. All right, so my idea for a basis is the following. Take the function x squared, x, and 1. All right, so as an exercise, prove that this is a basis for P2. In other words, check linear independence and check that it spans the entire space, meaning every single polynomial in P2 can be written as a linear combination of those three polynomials, x squared, x, and 1.